in the new year, so to say, but the last seminar in our academic half of the year. So I'm looking forward to see you, whom I can see, or to hear you, whom I can hear. I would like, by wishing all of you all the best for the coming year, fruitful new year, lot of optimism, which I think we will need, and first of all, good health. So let us now go directly to our program. I welcome Jonáš Kulhánek and Vojta Hudeček, those who are the authors of the talk. And please, I don't know who will start, but just start. Thank you.
Okay, I will start. Thank you. So welcome everyone to today's talk. First, I would like to join the wishes of Professor Hajčová and wish everyone Happy New Year and a lot of health. And thank you for joining us today for the talk. We are going to describe our end-to-end dialogue model based on the GPT architecture, with which we participated in end-to-end dialogue modeling shared task. So first, let me just briefly introduce ourselves. My name is Vojta Hudeček, and I'm doing PhD with Ondra Dušek here at ÚFAL. I focus on dialogue systems, on training dialogue system with less data requirements and less supervision. And my colleague Jonáš is our master student who is doing his master thesis also with Ondřej Dušek, and his master thesis topic is closely related to the project that we are going to describe today. So first, I'm just gonna give you an outline of today's talk. We start with the introduction and description of the end-to-end dialogue systems, its advantages and disadvantages. Then I will describe the challenge that we participated in. And then Jonáš will guide you through the architecture of our model and the results we achieved. And in the last part, we are going to give slightly more detailed analysis of our model, and we will be happy to answer your questions. Okay, so to start, today we are going to talk about task-oriented dialogue models. These models or systems are called task-oriented because they are supposed to achieve some specified goal or fulfill some task, whether it is a restaurant reservation or a hotel reservation, or it can be a booking of a seat in a train, etc. In order to achieve such a goal, we usually need to extract some structured information from the dialogue. So one of the main tasks of the model is to extract this information. Usually in the context of dialogue systems, we talk about slot filling. So the slots can be, for example, in the restaurant reservation domain. The slots can be price range of the restaurant, the area where the restaurant is located, time of the reservation, etc. And the system needs to find out what are the values for these slots to fulfill the user wishes. And another important notion in the area of task-oriented dialogue is that usually we need to somehow interact with the database we need to construct a query based on the current slot values and then obtain the relevant results. A traditional approach to such a task is to construct a kind of a pipeline architecture that consists of multiple individual components. Usually we see component for language understanding that transforms the natural language utterances into structured representations. Then we have some component for so-called state tracking, or sometimes we talk about belief tracking, belief state tracking. This component is supposed to summarize the dialog history and all the slot values. Then we have usually have a policy component that decides the next system action. And finally, some language generation component that verbalizes the actions. The problems with such an architectures are several. Firstly, it's prone to error accumulation. If there is a problem in some of the components, the rest of the components might have, it's difficult for the rest of the components to recover from the error. Also, the flexibility of such systems is limited. This means if we want to extend the functionality of our system, usually we need to retrain all the components individually, and it's quite demanding. And also sometimes we want to extend the system to cover more domains. For example, we don't want to only cover the restaurant reservation, but also want to take care of the hotel reservation. And in such cases, again, it's quite demanding and difficult to retrain such a pipeline system. So this is a motivation why the researchers focused on end-to-end dialog systems in the recent years. Also, one of the reasons was the growing success of neural network-based architectures that even allowed to create end-to-end architectures such as the one we are going to discuss today. So one of the first approaches was to kind of keep the modular structure of the system architecture and just join all the components so they can be trained jointly. We can see an example of such an architecture here on the slide. And we can still see a component for language understanding, belief tracking, and the policy, etc. These modules can be trained jointly in an end-to-end fashion, which is good, but it still needs a lot of annotation. Basically, you need still annotation for each of the components in the network. A new approach was introduced by the authors of the sequicity framework. They did two significant changes. First, they changed the representation of the belief state. The structure of the representation was flattened. So instead of using for each slot specific representation of the slot and its value, they just represented the belief state as the sequence of tokens that actually were the slot values. So the state is now represented just as a sequence of slot values, which is much simpler than in the previous case. And this allowed them to model the whole dialogue basically as a sequence-to-sequence problem. And in this period, like 2 or 3 years ago, there was a huge success of sequence-to-sequence neural models for machine translation, and many other tasks. So the authors took advantage of the success of these models and casted the dialogue response generation as the sequence-to-sequence problem. However, they needed to make some modifications, and they modified the decoding process. So instead of just one-stage decoding, the decoding actually consisted of 2 stages. In the first stage, they decode the belief state, and based on this, they can query the database, which is necessary to accomplish the task. And once they have the database results, they can condition on this result and on the decoded belief state and decode the final system response. Also, in this architecture, the language understanding component is not explicitly present. It is just done. It is done implicitly as we see the correct slot values in the belief state. So this training data for this kind of model requires less annotation. And basically we base our architecture on these ideas. Jonáš will talk about more details in a few minutes. Okay, so this was just for the introduction to the problematics. And now I'd like to talk a bit about the challenge that we participated in. That was the Dialogue System Technology Challenge. This is actually a regular workshop focused on various challenges in the dialogue research. It was its 9th iteration. Some of you might know the Dialogue State Tracking Challenge. And this is the same event. Firstly, it was focused only on state tracking in the first years, but later the range of topics widened, so it was renamed to Dialogue System Technology Challenge. And this year there were several tracks, and we participated in the end-to-end multi-domain task completion shared task. In this task, the participants were expected to take natural language utterances at the input, and the expected output was again a response generated in natural language. There were basically no restrictions on the model architecture, but the only restrictions were that it should take natural language and output again natural language. Also, in general, participants were allowed to use any training data possible, but the main data set used in this shared task was the MultiWOZ dataset. This dataset was collected in 2018 by the group of dialogue researchers, and since then it became quite well known and standard evaluation benchmark for task-oriented dialogue systems. It is in the tourist information domain. Tourist information domain in Cambridge. So the task of the system here is to provide the user with information about restaurants, hotels, public transport, or taxis. The data set consists of over 10,000 dialogues in 7 domains, and most of the dialogues are multi-domain. So we can observe more than one domain during the conversation. Apart from providing the necessary information, the system is also supposed to make a booking if it is asked to. This is quite an interesting specific of this data set, that you need to somehow take care about booking the venues or the trains. What is challenging about this data is that you need to, or your system should be able to handle switching the domains. So as I mentioned already, during one conversation, it is common that the user mentions the reservation at the restaurant, and then he or she wants to also order a taxi from the hotel that he stays in, and the system needs to react to all these requirements. And also the database integration is included. The database was included in the training data, and your system needs to be able to interact with it. And I also want to mention the evaluation scheme. There were two main methods of the evaluation for the shared task. First, it was an automatic evaluation that was performed by an automatic platform. That was, each participant was provided with this platform, so the participant could estimate the quality of their models using this method. The automatic evaluation was done with user simulator that was trained on the MultiWOZ data, and it mimics the behavior of the user based on the training data. So the user simulator can ask about restaurants, hotel, can also ask for bookings, etc. And your model should be able to interact with it. And the platform then also takes care about the evaluation of the metrics. One of them, or the main metrics used to evaluate the system, were the success rate. The success rate expresses the percentage of dialogues that are successful. Dialogue is considered successful if all the entities that are informed by the user are captured correctly also by the system. It also, if the user asks for some booking, the system should be able to do the booking in the successful dialogue. And lastly, if the user requires more information, the system should be able to provide all the requested information. If all these conditions are met, the dialogue is considered successful. There was also the book rate that only focuses on the dialogues in which the user or the user simulator asks for the booking and checks if the booking was done correctly. So if the venue that was booked corresponds to the user restrictions. And they also evaluate the blue score that is supposed to capture the fluency of the dialogue. Each participant was allowed to submit up to 5 different variants of their models. And after submission, each of these models was evaluated with this automatic evaluation scheme. And the model that scored the best was then evaluated with human judges on the Amazon Mechanical Turk platform. And this human evaluation was the final score that was used for ranking the models in the shared task. So this was to introduce the challenge, and now I'd like to ask Jonáš to tell you a bit about our approach.
Yeah, thank you. Good afternoon to everyone. Can you hear me, first of all?
Yeah.
Yeah, okay. Um, I will start by presenting the architecture of our system. So as Vojta already said, the system uses like cyclicity-like architecture. Like um, the architecture first decodes the belief state, which is then used as to query the database, and then uh, we use a language model to generate the final response and incorporate the database results into the final response. And in order to model the response and to um, to have like a good natural language response, we use GPT-2 language model because it was trained on a huge number of data, huge number of text. So it generates like good responses that sounds natural. And so this is basically the solid architecture. It uses GPT-2 uh, to generate the response. And also the same model is used to generate the belief state. So in order to generate the belief state using a language model, the belief state is first encoded into a string, and then it is passed to the database, and based on the database results, the final response is then generated. If you can go to the next slide. Uh, Here we will see that in more detail. First, the context is used as an input for the neural network. Now the context is just past utterances, and so the GPT-2 model then generates a belief state that can be seen in the gray box at the top left. This belief state, this belief state is then used as a query for the database. Database then returns the number of matches, and this is used as the input again for the same language model. So we use the context, the belief state, and the number of database results as the input for the same language model, and then the language model generates the response. Now the response can be seen in the bottom right box, the yellow one. The response is the lexicalized, which means that we replace any concrete values like hotel names or restaurant names, etc., by general tokens. Like you can see their destination, which and these tokens are then replaced by the database results to concrete values. Like this destination is then replaced, for example, with Cambridge. So this is the basic model. Now in these systems, we have to like the GPT model is quite big. It has a lot of parameters, and dialog data sets are usually small and noisy. And so in order to use these data sets with these big language models, we have to take care of several things. So what was used in Soloist, and we use it also, is that they used auxiliary tasks, each having its own loss, which is then added to the total loss, so it guides the gradients in the correct way. And what they did is that they predict the consistency of the dialogue. Like they generated some negative samples where they corrupted the dialogue, and then trained the binary classifier to predict whether the dialogue was tampered with or not. And we use like similar consistency detection task, slightly different, but I will talk about it later. And we also tried using classifiers to predict or to detect user intent and system actions. And these classifiers were attached. They were like linear classifiers attached at the end of GPT to representation. So now, in order to generate the belief state, we used greedy decoding, and to generate the final response, we used nucleus sampling. If you can go to the next slide. Yeah. Here we can see our representation of the belief state, the database results, and the lexicalized response. We choose this belief state representation because it contains a lot of natural language words like arrive by, leave at, etc., which is different from the slot names in the dataset, but we think that this may help the pre-trained model to use its like internal learned representations of these tokens. So this is our example of belief state, and on the line below there is like this DB. So this is the database results representation that is used as input for the model, and we also use a representation that is close to natural language to help the model. And then you can see the lexicalized response, where we just replace um, all the concrete values by the tokens. Can you go to the next slide, please? Okay, so we had to do several other things to help our model use these small and noisy datasets. And so we also used the consistency detection auxiliary task, but in the original Solist paper, they just swapped the whole belief state, or swapped the whole database response in order to generate a negative sample. And we instead, what we did instead was that we just replaced the values in the belief state by different values, because like learning whether the dialog was corrupted was easy for a model, because it just recognizes that there were different domains in the context and the belief state. So the task was really easy. And when we did our different consistency detection task, it was much more difficult for the language model to detect, to correctly say whether the belief state was matching with the rest of the context. So that was one thing that we did. We also extended the training data that we used. We used the data augmentation via back translations. Essentially, we used we used the language models to translate the whole data set to a different language. We used 10 languages for that, and then we translated these text back to English, and to generate paraphrases of the same text. And when we trained, we randomly sampled from these paraphrases and use these random paraphrases for the training. So we essentially enlarged our training data, and we also used the unlikelihood loss to increase the output diversity. Unlikelihood loss just penalizes when the language model uses the same token multiple times. So it is used to increase the diversity of the text. So we use it to just for the response generation. We also differ from the Solist in the way that we use different decoding strategies for the belief state and the response. Whereas in Solist they use always nucleus, and but we use greedy decoding for the belief state generation. So we found it to be like to have better performance. Also, we train our model only on what we call clean samples. That means the samples that are consistent with the uh, the goal. Like if we use the metrics from the MultiWOZ, these samples would have success rate 1. All other samples, in all other samples, the human annotator did some mistakes or didn't do the dialog properly. So we used only like 70% of the dataset, which were consistent. And we found out that this actually increased the performance of the system, just training on a small number of data, but clean data. So if you have any questions about the architecture, like now would be great time to ask. If you didn't catch something or don't understand how some part of the system work. No, okay. So maybe we can go to the results, and then later you can ask anytime. So first, we evaluated our system on the MultiWOZ dataset using the original MultiWOZ metrics. So just to remind you what inform and success means, and like inform is whether the system provided the correct or used the correct entity, like when the user asked for a train that leaves after the time the system was considering these trains that leave after the specified time. And success means whether the system outputted every requested information that the user asked the system to return. And so we compared our system to several other end-to-end systems, and we can see that our system outperformed other systems in essentially almost any metric except for the blow rate. So that's yeah, that's it. If you can go to the next slide, please. Yeah, here we can see the evaluation of our system in the DSTC. We are the team 7, and I will talk about the evaluation later, but basically we placed third in that competition, and these are the results. Now, if you can go to the next slide, please. Now, here are the results on the ConvLab 2, which was used for the automatic evaluation in a DSTC competition. And there are several other papers that used the same evaluation, and we outperformed the other method that published their results by a wide margin, I would say. And the here the problem with the ConvLab 2 evaluation uses their own like user simulator, and this simulator is then used to evaluate the system, the dialog systems that use that simulator. So maybe you can go to the next slide. Yeah. Here we tried several variants of our model and compared them with the baseline. You can see on the first row, it is our final model that was the best. But yeah, and we tried like turning off our modifications. So when we turned off unlikelihood or used the whole data set, this is denoted clean. And when we turned off unlikelihood and used the whole data set, or when we used these user intent and system action predictions, we can see that predicting user intent and system actions did not help the model much. The next line is when we used pre-training, when we did not use pre-training, because in all other models we pre-trained the model on big data sets like Taskmaster and Scheme Guided. And in this particular setup, we turned off this pre-training and trained it only on the MultiWOZ dataset. And in fact, this model that without pre-training was used in the DSTC competition. In the next line, there is the model without translation with alt consistency, which corresponds roughly to the Solist architecture, but we also use like clean samples and all other improvements. But just we compared the variant with the alt consistency and to see whether our consistency detection was better. And then we used variant without consistency. Now, if you can go 2 slides back to the human evaluation, yeah. Unfortunately, like we for the competition for the DSTC shared task, we sent 5 of our models, and 4 of them used pre-training on a big data set, and 1 did not. And the one that did not use the pre-training was the best in the automatic evaluation, because it was like more fine-tuned to the convolve evaluation task, and therefore this model was then used for the human evaluation. But unfortunately, this model has also the worst performance when we consider the response like naturalness. The when we tried these models, like this model seemed most unnatural um, for human. So that was quite unfortunate. So these results in this table are with the model that did not use pre-training, and all other results in all other tables, these models used pre-training. Okay, so that would be all. And so do you have any questions about the results or about the architecture?
Okay. If not, you are still welcome to ask at the end of the talk. Now, thanks, Jonáš. And I will just, in the last part, I will talk a bit about our error analysis. So we were interested to get more detailed insight into our model behavior. So we decided to perform more detailed manual analysis of the results. We looked at the MultiWOZ dataset and the way it was generated. So it was actually generated by created by humans who performed the dialogues according to some scripted scenarios. These scenarios wasn't scripted like word by word, but they were kind of bullet point lists with uh, the tasks and the specifications what the user should ask the system in the respective dialogue. So we took these bullet point lists, and according to these lists, we interactively performed 130 dialogues with the model and evaluated the results. So we looked at the kind of errors the model made, and somehow categorize the errors to several classes and analyzes the results. Out of these 130 dialogues, 50 of them contained some kind of error. However, some of them were still recoverable, so not all of the 50 erroneous dialogues ended as a failure. In fact, we recorded a success rate of almost 87%, which somehow corresponded to our result in human evaluation. However, it should be noted that this success rate is with no database grounding. That means we didn't check if the booked entities were correct, if the venues corresponded to the user needs. We only focused on the dialogues themselves. So here is the short summary statistics and distribution of the errors. Out of the 50 dialogues that contained some error, 17 of them ended as unsuccessful. And the most common type of error was in the belief state. So somehow some slot value was not correctly captured or somehow was missed. The second most frequent kind of error was the policy decision. So the system decided to take or to output a response that wasn't relevant under the respective dialog context, but most of these errors were recoverable. So you can see only 2 of them ended as a dialog failure. And we also recorded some errors that resulted as a bad database interaction. And we also have more detailed description of the errors. So the most common, again, was problems with the belief state. And most often we have seen something we call hallucinated values. This is a situation in which some slot value is not grounded in the database or in the dialog context. That means the model never saw the value for some slot, but it somehow made up the value. I will show you some example of this situation in a bit. And also, yeah, we recorded problems with lexicalization. That is a significant part of our system, and we found out it was problematic to implement the lexicalization correctly. And there were other problems, such as missing information, which we have an example of the missing information situation too. In this situation, the system forgets to ask about some necessary information. It needs to end the dialogue successfully, but it just skips the information and still ends the dialogue, which is not correct. And there were several other less frequent errors. Now let me just show you some of the examples. So in this dialogue, we can actually observe 2 kinds of errors. First is the bad domain recognition. So the user is asking for a theater in the Cambridge, and the system offers some options and asks about the preferences, and then offers a specific venue, the ADC theater, in the city center, and asks if the user needs more information, but the user actually wants to book a hotel. And now the system fails to capture that there was a change in the domain focus, and we are not anymore talking about the attractions, but it still responds, it still focuses on the theaters, which is wrong in this context. And so the user finally needs to specify explicitly that he or she is looking for a hotel. And finally, the system was able to capture the correct domain focus. And here actually comes the second error. So this dialog was really bad in this aspect. The system offers some hotels in the north part of town, but this is an example of hallucination because it wasn't mentioned in the dialogue so far that the user is interested in the north part of town. So the system kind of uh, assumed this area of town, but had no grounding for this value. And second example is an incomplete dialogue that somehow the user first asked to book a seat on a train, and then the seat was booked, and the user also asked for a booking at some Indian restaurant. And the system correctly asks about more specific information for the booking, such as what day should be the making the booking made. And the user said, okay, it's the same day as the train, which was Sunday, and it will be for 1:30 in the afternoon. And now the system was supposed to ask for how many people the reservation should be. But here in the belief state, we can see that the system inferred the number of people from the previous train reservation, but didn't really confirm with the user, which is wrong behavior. It's possible that the user wanted to reserve the table for 2 or more people. So the system just skipped this information and booked the table, which was wrong in this situation. Okay, so these were the errors we encountered. And now I'd just like to conclude our talk. So to summarize, we achieved state-of-the-art performance with respect to the inform and success metrics on the MultiWOZ 2.1 version of the dataset. As far as we concern the reported results. We also participated in the DSTC9 end-to-end task-oriented challenge and placed third in the final human evaluation. And we also was one of the only 4 systems that outperformed the baseline on the human evaluation, which is actually nice. And finally, we also performed some more detailed analysis that provided us with more insight into the model behavior. And based on that, we have some clues what should be improved and what are the weak points of our system. We have some plans for future work. We want to mainly experiment with latent representations of the belief state that should allow us to somehow bypass the noise and the error or not correct annotations in the data and make the model more robust. Related to this is also that we want to replace the lexicalization, which is now deterministic, but we have encountered a lot of problems with the lexicalization. So we would like to experiment with some trainable component that would replace our deterministic approach. And one of the possible options is also to experiment with explicit domain embeddings that would allow us to unify the training data sets and exploit more training data. So this is all for us for now. The source code will be published at our GitHub page after our paper will be reviewed in February. So now it's a good time. If you have any questions, we are happy to answer them.
Yeah, thank you very much for a very interesting